Okay, so let's continue to talk about the next topic on the gradient boosting. So let's and let's using and the regression problem as like one of the examples, regressions. So what it's doing is, say you have a set of features X and the target variable Y. So basically you have a pair of data. So this is my data. So basically we want to find out some kind of dependencies of like the model is like we want to find out Y is a function of fx, right? So the way that we're going to do is we're going to create some like loss function with Y is our target and my fx is our predictions. I want my Y is as I want my fx is as close as Y as possible. So this is like bunch of different like loss functions that you can choose. But the key is I want to find out fx such that to minimize this my loss functions. Right, so this is my f hat x. So this is almost everything in machine learning. It's like, I'm all like that. Up to now, we don't make any assumptions for this type of functions or models of fx could be arbitraries. And we didn't make any assumptions on the models of our approximations of like f hat and how to and achieve these things. So this is very general. And we didn't actually make any assumptions for the distributions of y as well. I mean, the only thing that we make assumption is we want this loss function to be differentiable. L is differentiable. So which is like, and most of that will be, and okay, for example, we are working with the mean square loss. So what we do is, and we have all these x, y is being sampled from certain like and a certain like and distributions. And what we can think is we can further generalize to think about this is the following way that we actually define. So because, and if we try to minimize something like this, the issue is if we change our and a data set D, then my fx hat will be different, right? Because we assume all these x and y as example from some distributions. So if we want our f hat to be all fixed, so that would be and we can like to take and a certain like and expectations if we want. F hat of x is argue mean of fx, expectation of x and y. So basically, we take the expectation of the distributions of x and y's. Okay. So, but this issue is this whole thing is nearly impossible to solve because it's just like there are too many choices, and the whole thing is basically infinite dimensional. So what we do is, I mean, this whole search space is too large. So that's why we need to limit our search space to some family of the functions. So then the next is we're going to and this is something to make sure this fx is I mean it's respected to the distributions. But right here on that is we assume this fx has some parameter of theta. So family of functions. So this is like some parameter that we can learn here. So this theta is something like in R small d. That we can learn that. Such that we don't actually need to search complicated and functional space. We just trying to solve the optimal parameters. So basically my then in this case is then my f hat of x is just the optimal parameters for the family of functions. Okay, so this whole thing becomes trying to find out this optimal parameter instead. Argue mean of theta of expected value of x and y of L loss functions between y and x theta. So if we think about a family of function, this is basically equivalent to say we choose certain type of models. Like for example, say like and the linear regressions, could be logistic regressions, could be like and all sorts of different models. Right. So this is basically and almost all the models they have some parameters that you need to learn here. Okay, so then this is the whole idea. And then we are ready to introduce the first one, which is gradient boosting. So like gradient boosting is like ADA boost, and which is also boosting algorithms. And you can also using like and boost the trees, and it can be constructed through in the training process. So and a boosting and a gradient boost. Okay, so what and what and the and the whole idea is very similar to and the whole thing is quite close to ADA boost. But there's slightly difference here. So and we're trying to find out this fx, which is again is the linear combinations of and a bunch of others. Rho of I, t of x, and theta of I. So basically these are and basically a family of functions, but evaluate at like theta I. So and what you do is you are going to find out this like theta 1, theta 2 to theta m, and the current trees is going to be trained based on the result of previous trees. So this is very similar, and the whole idea is very similar to the ADA boost. So and the whole idea is basically the training process is basically and it's basically the forward stepwise. Right, so basically, and the current trees is being trained based on the result of previous. All right, so and here we have like and the number of trees that we have is the m. So and we have m in trees that we need to be trained. So the whole idea is given as follows. So the first thing is we set the initial tree is my f0 x is just a constant, which is lambda. And then we are going to adding these trees and gradually. So for I is equal to 1, 2 to the m. So what we do is we're going to find out fi of x equal to fi minus 1 of x plus rho of I tx theta of I. So basically what this is doing, I mean fi minus 1 is the model that has been trained in the previous round. I mean the current training round is to get optimal value of theta I, that we can get the current, like, and say for example decision trees that minimize the certain like loss functions. So and the whole idea is and objective is to train and train these T's. Okay, and also the rho right here. So this is the objective. So how we're going to find it? It's basically we're trying to do the following optimization problem. This theta I hat and rho I hat is equal to argument of theta I and the rho of I of loss of y fi minus 1 plus rho of I tx of this. So basically you should and the point is you want to find out the one additional and one additional trace and optimal parameters for one additional trace. Then we go through this whole thing, and you can see right here is the key. And I'm going to tell and mention what kind of and the loss function we're going to choose and how to get this optimal theta I and the rho I. I mean, here we're just trying to give you a good idea of what we're trying to do here. And then the final one, and then the final one is just then you sum all this together, then becomes fm of x equal to summation I from 1 to the m, then rho I t x theta I hat. Okay, so the major differences is and between the ADA boost and the boosted trees gradient boosting just lying right here. Okay, so and let me show you what kind of the loss functions that we can choose. And later I'm going to show you and how this actually being done here. So for example, what we can do is we can choose, and for example, we can choose the square loss. So that means this, for example, this my L of yfx is equal to 1/2 of y minus fx squared. Okay, so I'm basically a square loss. So you can plug in at I step because now and And so this is my NFX. So this is basically at I step. So you are getting something like Y and FIX. Okay, so this is 1/2 Y minus Fi minus 1x minus rho of I T x theta I squared. So this is basically, if we plug in here. So at this point, we know the Y, we also know Fi minus 1 because that's what we already know up to the step of I and I minus 1. And then what we have is basically we're trying to optimize the following thing. The theta I is what we're trying to is argue mean of theta I of basically we're trying to do, and we need to plug in the data, right? So we need to plug in the data. 1/2 summation n from 1 to capital N, and we have yn minus Fi minus 1 of x of n squared. Sorry. And subtract. And we can absorb everything. And we can like ignore the rho for now. Then just say this is being minus t of x of n and the theta of I. Okay, so this is basically what you are getting here. So that means at each training step of I, what we actually needed is this residues, which is y minus of Fi minus 1x as our target for the new model of our T's. So we are trying to train our new model for the residues. Right? So this is, I'm actually the residues. So we're going to add one more trace of the new model, trying to approximate the residues of the previous model. Okay, so this is very, very reasonable. So once we find out in such kind of theta, so the step 1, then we find out the theta first. Then step 2 is we need to find the optimal coefficient of rho I. So this rho I is like we trying to do this line search. That means we are going to add this t and with the optimal parameter of theta I, but we are not going to add as a 1. We are trying to find out the best parameters along the way. So this will be argued mean. So you can think about this is we're trying to do the gradient descent, and the loss is like decreasing and along, the directions of the gradient descent. But the issue is we want to find out and what is the optimal time step such that this learning rate is optimized along the directions of the gradient descent. So this becomes, I'm going to try to do this L of y of Fi minus 1 of x plus rho I t x of theta I hat. So this is basically we're trying to find out this time step. It's like a line search. So this whole an idea is and very much the line search. All right. So, but of course, if we have a more complicated loss functions, and how can we do this update, right? And for now, and for the and the square loss, we somehow and figure out this is related to trying to approximate the residue. It's kind of like gradient, right? So you think about it's like gradient descent, but that's like a gradient descent in the directions of the functions. So for example, and you can choose a different and choose a different loss. For example, you can choose absolute values and absolute loss. Right. So what does that mean? Is my loss looks like this. Which is totally possible. But how can we update that? Right. So then this update target is no longer being the residue. So we are not trying to approximate the residue. So what we are trying to do is, I mean, if we're using different losses, and how can we just try to update things and accordingly? So this whole idea is we should think about to come up with a negative gradient of the loss functions with respect to knob and the models. So we should use and always use and generically use the negative gradient of the loss functions. And respect to the models. Basically, it's a minus partial L of y and fx partial fx. So this is basically, it's like a gradient descent, but in the directions of the function of fx. So this is, I mean, slightly different. And of course, if we choose the and special cases that we have for L is being the square loss, that means 1/2 of y minus of fx square. Then this minus partial L partial fx is nothing but your y minus of fx. So which is just precisely is the residue, which is our like negative gradient. However, if we choose our loss to be the absolute loss, as I mentioned, this is y minus of fx. Then this negative gradient, which is being the sign of y minus of fx. And of course, there are many other losses that, and you can choose, for example, and we can choose the Huber loss. Or we can choose something called quantile loss. For each loss, I mean, in the notebook, you can go back to check what is this loss and what is the corresponding negative gradient. So the whole idea and the reason, and we have a multiple and the loss functions is like, and there are difference and advantage and disadvantage of the loss functions. So basically, the common way that we can choose the square errors, and these square error will amplify. But the problem for the square error, it will amplify the errors that is greater than 1. So that means it will be more sensitive to outliers. So this is a common problems like in the linear regressions. So and what we can do is we can choose the second one, which is using this absolute error to avoid these problems. But they might have other issues. For example, this is not always gradient. And the gradient, it's not always exist, because if it's just precisely equal to 0, then we have a problem. And so like it, and that's also, and another thing that is possible, it might and we're trying to do this an approximation, it might cross the minimum point easily, and because the gradient that we get is very big, even like very close to the minimum point, because the gradient that we got for this absolute error, it's either +1 or -1. So there's nothing in the middle. So that means if my solution is getting very close to minimum point, my gradient is still +1 or -1. So which means that we are not getting some idea that my gradient is close to. And my error is close to the minimums now. And so the reason that we choose and Huber loss and the quantile loss, it's also very similar to the reason that we're using absolute loss. Is both log and the loss can like avoid the influence of the outliers. So that's basically and the whole idea of how we choose this theta and the rows here. So I'm going to tell you one thing, which is and the biggest difference between this and the gradient boosting and ADA boost. So, and the major differences is if we're choosing this like square loss, I'm going to talk about this, just focus on the square loss. The ADA boost is we focus on the misclassified points. It's basically we take a bunch of exams, we make mistakes on certain points, then we're going to to add more weight for those points that we make mistakes. And in the next round, we are going to more like inclined to correct those points that we make mistakes. So this is the major and the major benefit for the ADA boost. However, on the boost trees or gradient boosting is we're trying to focus on the differences between the current model and the target. So basically, we're trying to focus on the residues. And the training object for the next round model is to reduce the differences between the models and the target. So that means we're trying to reduce and trying to reduce the residues. And also various different and gradient boosting will be different if we choose a different and the loss functions. So that's why and everything will lies in this. I'm just trying to give you one specific examples if we're choosing and a square loss. So one of the commonly asked questions in data science interviews just to talk about what is gradient boosting, and what is this is like exactly doing right here. Okay, so that's obviously very important. So let me just show you what is the what is the classic version of the gradient boosting methods. Wait, let me just show it back with. Right here. Okay, so this is the Fredman and the classic algorithms of the boostings. So basically, we have a training data set. We have number of iterations of M. We have a choices of functions, and just could be and a square loss, and we need to choose a function family of based estimators. I mean, it could be just like decision trees, like what we have, and what we have talked about that. And also like there are some like hyperparameters that you could possibly tune, for example, and the true depth, and the depth of the and the like depth levels of the decision trees. Okay, so what we do is we need to start with F0, which is the initial guess. So as I mentioned, this will be guessed as a constant. So it's just a gamma here, right here, and which is a real value. So what we do is for this initial approximation, we only consider a constant value gamma. So what we do is we try to find out the gamma that actually so minimize the whole and the whole lot functions. So you can think about a natural way. So we can using just a straight line or the mean, trying to approximate and everything's and that we can have. So this is the most crude version of everything. So basically, we're trying to find out the gamma and actually minimize the square loss. I think, equivalently, they will be just taking the means of the and the y values right here. Okay, so everything is basically the same. So we calculate this negative gradient and a derivative, evaluate f equal to f hat, and which is the previous and the models we already find. Then we build a new base estimator. It could be just decision trees as regressions on this like residues. Then we find out optimal coefficient for rho, and then we and trying to minimize these problems. And this whole thing, it's very like the line search and optimizations of the gradient descent methods. Then we're going to add rho I and t and the theta I. So like both rho I and the theta I will be just being the optimal and the parameters that we find it out. So and this is basically the diagrams that we have. So basically, and this is the whole idea. So and at first that we have a new target, and target of y1. Then we through training we find and weak learner 1. Then we make the predictions and we have some predicted values. So then we create a new loss, and a new loss, and then we have a new target, and which is our residue. Then we train another weak learners trying to approximate the residues, and then we combine them together to create a new loss, and so on. So at each step, the biggest differences here, as I said, is we're trying to approximate the residues here. So this is basically the class functions that we have. I don't want to get into too much detail, but this is basic says how we actually implement everything from scratch. So we can do some very very simple and examples. So you can see, and the most important things right here is we need to stop and we can do some like cross validations, and we need to like stop early if we keep adding the new estimators, it's possible the validation errors start to increase because your model is getting more and more complicated. And what you do is you should always keep a validation data set to do some like validation testings. So you should just and you should stop if you see the validation and error start to increase. So and you will say, okay, and training stop and then you just cut off. So we are not going to adding more and more trees, because we know if we're adding more and more trees, you are likely to get an overfit. So this is very important that you need to split your training and the validations to ensure you will not an overfit, and we need to apply this like early stop and strategy here. So this is basically, and the data, you can see this data is very noisy and very hard as well, because the first part of the data is actually, I mean, straight line, but with like, and less variances. But in the next one, it's like, it's bigger and larger variances. But I mean, still a straight line. But you can see this is a very, very difficult model to approximate. And although, I mean, that will be a straight line, but noises will be not homogeneous. So this is very tricky here. Through this, we find out after 10 rounds of this, it will stop right here. And once we plot this predict data and versus true data, you can see this has a lot of like and zigzags. And after like in the later part, we know and the noise is bigger. However, right here in the first part of the data, and then the noise is small, so you can see, I mean, this is almost a straight line right here. Okay, so and of course you can make things more and more complicated, and you can try to see whether and this is giving you a good result or not. Yes, you can make this like and this make regressions. You can see right here, and the final and the testing data set is, and the test error is like 4,300 right here. And you can see this is doing like pretty good job right here. And for this data, and this is like much more complicated and the data, and then we have like 10,000 data sets and 50 features, and this data is much more important and much more complicated. And we have more data, more complications, and actually we stop at like and almost like and the round of 145. And we test with the testing errors, and you can see this test error is quite close to the validation error. So and we are very satisfied with that. And also, and this is basically the regressions, and we can do very similar things for the classifications. Just classification is, I mean, this is basically the diagram for the classifications. And it's very, very similar. And this can also be done with and gradient boostings. And basically you can think about is basically and several sets of and the regression trees can be just numbers of the categories, and each set will like represent a category. Then you are going to output all the set and transform into probability distributions using the softmax. So basically each set you are going to output a value. It's like regressions that we already have. And after that, we're going to take the softmax and turn all these values into probabilities. And also then basically the negative gradient of each tree is being calculated using something like cross entropies or KL divergences, like what we like what we have done on like and the logistic regression or the SVMs. And this is basically the guide and the guidance here. So basically, and everything right here is very similar to the regressions. But the difference is after that, we're going to take these ensembles for this and outputs. Then after that, we're going to take and the softmax layers. Then we'll output the probabilities, and through the probability, it will output and which like labels will be predicted out. Okay, so I mean, so naturally you can turning a regression problem into classification problems. And of course, and that will be and your softmax that you're going to come up with, and this y1 and to yn is and your labels, and y here will just be one hot encoding for the labels. And then and here we're trying to work with a cross entropy and a loss, and then you can just write down this cross entropy the loss functions, and explicitly, because this pi is given from the softmax functions right here. So this is being and given out like explicitly. After trying this expressions, we can find out this analytical expressions for this like loss function here. And the key here is, if we want, we can actually take the gradient of our loss functions with respect to and y hat, and we getting this so analytical way of our gradient. We can take advantage of this analytical way of the gradient and passing through, eventually we can switch the parameter in all these regression trees and find a way to tuning these parameters. So this is basically the way. We are still using the idea of the regressions, but using the output regressions, and then we apply the softmax, and then becomes a classification problems. Then after that, we can using these results and propagate backward to find out the gradient, and like what we had done before, and like what we had done before for those regression trees. So basically, this is the whole idea that we're trying to do here. I think here is the one simple examples that we already mentioned here. So this is and a data set like and a moon, and it's like make and a classification data set. Is we have a 100 data point. We only have 2 features, so that's why we can make a plot right here. But if we trying to do this and the boundary plot, you can see this actually create and the boundaries and very nicely, and you can see right here. And we are using this one-hot encodings, and saw the things that we're turning this classification problems into a regression problems. Then we can using this like and regression techniques we already did before. And also we can make this and a similar test with 10,000 data set and 50 features. So, and also the number of classes that we have is 3. Then we apply everything on one-hot encodings. Then we do the splitting, and we just and apply this like multi-class and gradient boosting and the classification problems. And you can see it actually stopped at 156 and runs, and we can see at this point the training is getting 0.99. It's almost like 100% of accuracy. The validation is getting like 95.4%. The test data and AUC that we got is 95 and 0.951, which is quite good. And you can see this is very much close to what we already have for the validations and the trainings right here. So this is quite good. I think that's reasonable, and it give you some idea what we're actually doing for the boosted classification trees. So with this and the videos, we have a talk about and gradient boosting, and with various different examples, and we talk about the ideas underneath of this, and also in the meantime, how to implement that from scratch, such that you have a very good idea on those algorithms with various different examples. Okay, that's all I want to talk about for this video.